In this example, we are going to be looking at how you can apply Charles' law. So Charles' law is the gas law that relates the volume of a gas with its temperature. So the question tells us to calculate the temperature required to cause 4.9 liters of a gas originally at 32.1 degrees Celsius to contract to a volume of 2.5 liters. Assume pressure is kept constant. So that's a really important piece there. Assume that pressure is kept constant. That's a good clue for us to know that we're going to use Charles' law and not a different gas law. So since we're starting with 32 degrees Celsius, we can start to make a data list. So that's going to be 32.1 Celsius, which we're going to have to convert to Kelvin. That's our initial temperature. The initial volume is 4.9 liters. The final volume is 2.5 liters. And the final temperature is what we're being asked for. So first, we'll just make sure that we get our temperature in the proper unit, so in degrees Kelvin. So we know that if we want a temperature in degrees Kelvin and we're given Celsius, then we will be adding 273.15. So the initial temperature is equal to 305.25 degrees Kelvin. So that's our initial temperature. So from there, we can then start to sub in some of our information into the Charles' law formula. So Charles' law is given as V1 times T2 equals V2 times T1. And then we want T2, or the final volume, on its own. So to make that happen, we'll divide both sides of the equation by V1. To get a new expression. And then we'll just sub in all of our information. So V2 is 2.5 liters. The initial temperature, 305.25 Kelvin, right? That had to come from Kelvin. All divided by 4.9 liters. So then we would type that into our calculator, determine a final result. And we would see that T2, or the final temperature in this situation, is equal to about 155.74 Kelvin. And then one final step for us here is we should report the final answer in the same units that we were given. And since we were given a value in degrees Celsius, we should report our final answer in degrees Celsius as well. So we'll convert this into degrees Celsius. And when we want to go from Kelvin to Celsius, then you subtract 273.15. And that tells us the temperature is minus 117.41 degrees Celsius. So that's very, very cold. Like, that is very, very cold. And that conceptually makes sense because we know that if the temperature of something decreases, then its volume is also going to decrease as well. So then we just need a therefore statement. Therefore, the final temperature required is minus 117.41 degrees Celsius. So it would be very, very cold. Theoretically, that would be a temperature that you might see in in like very specific laboratories, like in space, those kind of places.